namely a single underlying constraint that my scalar variable x should be equal to the scalar random variable omega, and in fact I have therefore randomness only in the right hand side. Matrix T doesn't depend on omega, it's just deterministic, it's equal to 1. And I propose that we consider the following value function of the second stage problem that captures our penalty cost, recourse cost for that underlying random constraint. And here it is, and the notation is supposed to be suggestive. What do you recognize? Do you recognize something at all? Is this familiar to you? I'm actually hoping that everybody would now say yes. Yeah, that's an application of a more general recourse structure, a special case that actually has a name. It's called simple recourse. Right? Indeed. We are looking at a second stage problem where we have indeed a single constraint involving two variables denoted by y plus and y minus. The idea is that y plus captures the positive part of z. If z happens to be negative, it's picked up by y minus. And I claim that given the specification here, that's indeed one example of the kind of models we've been assuming throughout, namely sufficiently expensive and complete. Question to you, is that actually true? Why is this sufficiently expensive? Why is it complete? Make up. Is it sufficiently expensive?
Yes.
Yes. Why?
Because it cannot be minus infinity.
Yeah, but that's essentially saying it is because it's true.
Okay. Because the Q's are bigger than 0 as the sum.
Right. Cost coefficients are non-negative. We know that's a special case guaranteeing sufficiently expensive recourse. So that side is covered. How about complete recourse? Well, I already told you that it's simple recourse, and in fact we proved that simple recourse is complete. Yeah, so indeed this is an example of the setting we have been talking about. So let's see what our analysis brings in this setting. Yeah.
Which would be y plus complete recourse.
Because it's simple recourse. And simple recourse is a special recourse structure that we recognize in general by this matrix identity minus identity. Well, here's just one-dimensional, but still. And we prove by this very nice dual characterization that this is indeed complete recourse. All right? Okay. So, given our assumptions, we have strong LP duality, so we can write the dual formulation using equality, which is straightforward, and we find that our dual feasible set is this interval -1, 1, which has two extreme points, namely -1 and 1. And that's what I write in the third line. Indeed, our value function v for this particular example is the pointwise maximum of two linear functions. One with slope -1 and the other with slope +1. And the picture is also included. Okay. And now I look at what are the subgradients of the underlying value function. Well, that depends. If I consider a z which is strictly negative, then from the formulation but also from the picture, it's immediate that the single extreme point, which is optimal, bringing that maximum value, is -1. Then again, if we look at a z which is strictly positive, again we have a unique optimal double solution, namely +1. Only if z is right in the middle, equal to 0, we have multiple optimal double solutions. Anything goes, as long as it's in between -1 and 1, which is our complete dual. that's an optimal solution. So in fact, our subdifferential in that case is indeed not a singleton, but a set. So far, so good. Then, of course, we make the next step, because we're not only interested in V, we want to learn about the expected version. So now I'm going to look at Q. And to do so, I need to postulate a distribution, and let's start easy. Keep it easy. I'm going to consider a two-point discrete distribution with two realizations, namely the values 1 and 2, and for simplicity, with equal probability, a half. And the question is, okay, what does that tell us about Q? What does that tell us about the subdifferential of Q? Because that's what we're after. And, well, to make that a concrete question, I'm going to consider that function Q in a number of arguments. And I propose to first look at x equal to 0. And it says there that I observe that actually that x is not in the support of that random variable omega. Indeed, 0 is not in 1, 2. Why is that useful to know? Because it tells us what we can expect. Because we, including you, know everything there is to know about simple recourse functions, right? We analyzed it in class, we looked at the other side of the medal, that function g, played with the examples on MATLAB, so you know everything and you can answer this question. What does it tell us in particular about the subdifferential in that point which is not in the support? What do we know about that simple recourse function Q? Why am I asking? Because it always helps to know what you will find in proving it, right? Who can give the answer? Let me be more concrete. In the neighborhood of this particular argument, x equal to 0, will we find that the recourse function Q is linear or not? Does it have a kink at 0 or not? You know it. You don't realize it, but you do. Okay, let's vote. Who says yes? It has a kink. At least one guy is brave. Who says no? Few people, most people do not have an opinion. Let's see. This is the full story. And there you see a picture of this corresponding recourse function Q. It is piecewise linear, as we know it is, given that the distribution is discrete. And we also know, and that was the point I was trying to help you with, is that only in points of the support, actually this function is non-differentiable. It's non-linear. It jumps, the slope jumps, exactly at 1 and 2, because that's where the probability mass is. Remember? Okay. How does that read in terms of our analysis? Okay, to find the subdifferential of Q, we take the expectation of the subdifferential of V, evaluated in omega minus A. Okay, and we know our general formula is in terms of the set of optimal dual solutions, and of course then applying the chain rule, which is just a minus 1 here. Okay, let's do that. We do know, just disappear. Okay, omega can take two values, 1 and 2, and x is 0. So, to calculate that expectation, we plug in both, multiply with probability of half, and for omega equal to 1, what do we find? Well, if omega is equal to 1, then 1 minus 0 is 1, which is strictly positive. So the subgradient of V is 1. Multiplied by probability of half, that brings a half, and then multiplied by minus t, minus 1. That's the first term. Second term I'm not going to spell out, but it's much the same thing. And then we add those two terms, and we find that The subdifferential of Q at x equal to 0 is a singleton. It's minus 1. Well, if the subdifferential is a singleton, it means that actually the gradient, the function, is differentiable there. And that matches what we already know, where on this part, where the function is indeed infinite. Bit more interesting is to say, okay, what happens if I pick an x which is actually in the support? For example, x equal to 1. I go through the very same steps, but now I find if I consider omega equal to 1, then the difference between omega and x is 0. That's precisely the point where that underlying value function has a kink. And we found that its subdifferential is there, the entire range minus 1 to 1. Okay, that brings, multiplied by a half, and, well, multiplying the interval minus 1, 1 by minus 1 doesn't do anything at all. You get the same interval. So that's the first term. The second, for omega equals 2, we have, well, omega minus x is then still strictly positive, so we get a single value, plus 1. And then we add, according to the probability weights, and we find that for this particular value of x, the subdifferential is indeed an interval between the two extremes, minus 1 and 0. And again, that doesn't come as a surprise, we already know that since x is in the support, in fact, the function q will be non-differential. That's confirmed by our analysis. And we now know the numbers. Indeed, looking at the picture, here's the slope minus 1, and there's the slope 0, and anything in between defines such a supporting hyperplane with the corresponding slope. Okay? And the last remark is indeed that, well, to get a concrete subgradient at this particular point, it suffices to pick just one point out of that full interval that I have in the first term. Any choice, combined with the second, will bring a subgradient from that set. Okay? Now this is really the easiest example I could come up with, and I hope it helps you in understanding what it is that we're looking at. Questions? Remarks? If not, then we continue and make it a little bit more general, but hopefully what we've done so far will help us. Here's the next step, as always. The easiest analysis is by looking at a discrete distribution, and that's what I propose to do here. Let's, under our assumption so far, namely that the value function corresponds to the second stage problem, which is sufficiently expensive and complete, so everything is finite. See what happens if the expectation is with respect to a discrete random vector omega. That is, we are given a finite number of possible realizations with corresponding probabilities Ps. Here we go. What do we need to do? Well, for a given fixed x, arbitrary but fixed, we need to consider each and every realization of omega. So omega 1 up to omega s. And for each combination, we need to find the set of corresponding optimal dual solutions, lambda star, which in general is not a singleton. It can be a collection of extreme points. And what we then do is pick just one element out of that set. Out of that set of optimal dual solutions, we pick one. And we do this for each and every realization omega s. Then we take the expectation, and what comes out is a subgradient of the recourse function q at that particular x. So the bottom line such a subgradient, we need to find optimal dual solutions. Because they will essentially tell us what the subgradient is. Okay? Now, of course, we make it a bit more difficult by assuming that the distribution is continuous. And that means we assume that the distribution is given to us, also including the probability density function, which I typically denote by small l. What do we know? Well, of course, we know the general analysis so far, but also we know a special case. We do know that in the simple recourse setting, which is indeed a special case, if the distribution is continuous, then we found that actually the corresponding recourse function Q is smooth. It's differentiable everywhere. Remember? So, as far as we know so far, and our intuition talking is that maybe we can expect to find a similar result in the more general case. We don't know yet, but that's the information we have so far. Okay. In an attempt to prove that, I'm doing the following, and let me warn you, what is on the remainder of this slide is again an attempt to help you give some intuition. It's not formal mathematics. For the formal proof of the result we will find, I refer to the lecture. Okay, so assuming that indeed the special case simple recourse is telling us the story about the more general case, I can set up the question, what does the subdifferential of Q look like in the following way? I say, okay, the subdifferential of Q is the expectation of the subdifferential of the underlying value function V. We've seen that before, and we argued that that's actually allowed to do so in this setting, because the functions are nice. And I now apply a trick. I say, okay, two things can happen, as we've seen before. Either it's easy, namely, I'm looking at V where it is actually differentiable, so I can talk about a gradient, and there's the rest. Namely, those points where the function is not differentiable, get nasty, so to speak, and I consider there, necessarily, the full subgradient. Right, the set, it's not a single from there. So, accordingly, I split up the expectation, more formally, I make a partition of the support omega in two sets. Namely, for a given fixed x, those omega where everything is nice, namely V is differentiable in the corresponding x omega combination, and the remainder I denote by omega 2, that's where bad things happen. Alright? Now, the main idea will be to prove, given that this is what we expect to find, that actually this set, omega 2, has probability 0. So I can forget about what happens there. You see that that would be helpful if we can do this. That would be a line of attack in proving this result. Well, prove. Okay. Yeah? Okay, let's see what we can do. So consider one element of this set omega 2, the bad guys. That means that our underlying value function V is by assumption not differentiable in that point corresponding to that optimization direction, bringing multiple dual optimal solutions. That's the setting. In a picture, it's something like this. This is, as always, our non-empty, bounded dual set. And apparently, we're in a setting where we're optimizing in a direction such that at least two, and therefore the entire interval of optimal of dual solutions are optimal. That's the direction. And now the argument I'm making here is to say, well, if that's true for omega bar, then the same holds for some positive constant, let's call it alpha, times omega bar. Why? Because that specifies exactly the same direction. It's just multiplication by positive constant. So, the reasoning is, apparently for each such omega bar, a bad direction, so to speak, there's a whole line of omega bars correspondingly, namely every positive multiple of that small omega bar. So that specifies a half line. Okay. Now I say, I don't care, that half line is lower dimensional, and since the distribution is continuous, that has probability 0. So one such half line doesn't hurt us. We can indeed conclude that the probability mass on that half line is 0, so let's forget it. But that's not sufficient because I just picked one omega bar, but now I say, well, actually, there are only finitely many of those directions, namely one corresponding to each face of that dual physical set. And that's, if you remember what we discussed before the break, typically we find that our value function v is differentiable. Only in that finite number of directions of optimization do we find multiple dual solutions. That's the same argument I'm using here, which tells us that indeed, actually the probability of that entire set omega 2, where the bad things happen, is 0. So, the conclusion is, to find the subdifferential of Q, I only need to consider that first term, that is the expectation over omega 1, where everything is nice, namely the underlying value function is differentiable, it has a gradient, and that tells us that also for the expected version Q, things are nice, as expected, or at least as suggested. The function is indeed differentiable everywhere. It has a gradient everywhere. As soon as we have that the underlying distribution is continuous. So, conclusion, like in the special case simple recourse, also in the much more general case, namely complete recourse and of course sufficiently expensive, if the distribution is continuous, the recourse function is smooth, differentiable, it has a gradient. Can you follow this reasoning? It will help you. I hope so. Because later, when we talk about algorithms, of course this kind of knowledge is highly relevant and we will use it in constructing our algorithm. Okay? I'm repeating myself because I do realize that more or less every lecture I say what I discussed today is extremely important, so please make sure that you know it by heart and so on. Today is no different. The final part of today's lecture is much, much easier. Namely, it's about this. For the last couple of lectures, we've been discussing technical details about to arrive at properties of that recourse function Q. But that doesn't take away the fact that we know that actually calculating function values, let alone finding first order information such as gradients and subgradients, is actually very, very difficult. If anything, what we discussed today should convince you that indeed it's not that easy, it doesn't come for free. All the more reason to say, if at all possible, I would rather not solve that difficult recourse model. It's if it is possible to get what we need, namely the answer to the question, what is a good solution, which is the optimal X or near the optimal X. If I can get to that answer with the less work, maybe very easily, that would be guarantee on how good actually that particular solution is. Okay, that's what's behind this story. Can we proceed as follows? Can we somehow, and that remains to be specified, in an easy way, get a lower bound and an upper bound on the optimal value of the two-stage recourse problem, that difficult problem that we're trying to avoid? The idea being, if the gap between the upper bound and the lower bound that we obtain in some way to be specified, if that gap is small, then we would be happy to say, okay, what we found using those easy means is good enough. Let's forget about solving the full recourse model. Of course, we would feel bad because solving that recourse model is still nice. But from a practical perspective, this would be very helpful. So, what I'm proposing is to look at the problem again and try to find a way to not solve it. That's a surprise, eh? Okay. Question to you is, what do we do? So actually there's two questions. How can we find a lower bound on the optimal value? And how can we find an upper bound? Let's start with the easiest question. How do you find an upper bound for such a minimization problem? This is not specific for this particular recourse model. In any minimization problem, what is the easiest way to get an upper bound? Nobody?
Just some feasible solution.
Right. Any feasible solution with its corresponding objective value gives an upper bound. That was easy, right? How about the more difficult question? And now I'm talking specific for this recourse problem. How can we make it easier and then hopefully find a lower bound? Let's split it in two questions. How can we make it substantially easier? This difficult stochastic programming problem involving the uncertainty. Think back of the very first lecture. Oh,
Just considering the discrete, not the discrete deterministic part.
yeah, which means in terms of the random variables.
So they don't satisfy the what you mean.
Probably you mean what I'm looking for, but I don't like the formulation yet, so other suggestions.
Take arbitrary points from the distribution, and then all those serve as an upper bound.
Yeah,
And
so
like all the value functions.
essentially sample from the distribution, that's what you're suggesting. It's still quite difficult because, well, we do not know for sure, but probably a small sample won't suffice. So we need a large sample and then it's still a difficult problem. No, I'm thinking much, much easier. If it's the randomness that makes it difficult, then what would you like to do to make it easy? Yeah, get rid of that randomness. How?
By solving CX and removing Q.
Just kick out Q. That would be a very crude approximation. I'm thinking just slightly more advanced.
Discretized distribution.
Yeah, but then still, I mean, if there are quite a few points in the distribution in the support, it's still a full-fledged recourse model, and that's still not so easy. Do the easiest thing you can do, that is capture that full distribution by its expectation. Because as soon as we do that, indeed we end up with a very easy problem, which we know under the name of the expected value problem. And this is what we propose. Replace the random vector omega given in terms of its throw away all that information and simply use the mean, the expected value of that vector. That means that instead of considering T of omega and H of omega, we simply look at T of mu and H of mu, which are just deterministic data. And then we solve the corresponding problem, still involving that value function, which penalizes deviations. And in fact, and that's something to discuss in more detail later, this notion of sufficiently extensive recourse can be sharpened a bit, and then actually we can guarantee that the solution that we find in this deterministic problem will actually satisfy those goal constraints T omega with all H. If the recourse is extensive enough. And from an interpretation point of view, that actually makes sense. Why? Because we kicked out randomness, and that randomness was actually the reason why we introduced the recourse cost. So intuitively, it makes sense that if there is no randomness, then we won't use. That's in the slide. Okay. What we end up with is simply this. And that we recognize is small relative to a large recourse problem with distribution. A small deterministic in the program, we can solve it. If we can't solve this problem, we can really forget about solving the difficult problem. So it's reasonable to assume that we can solve it. The big question now, of course, is if we do this, what do we get? Do we actually get a lower bound? Because an upper bound we already have, and we're still looking for a lower bound. So that's my question to you. What is your intuition? Will this bring a lower bound? And if so, can you argue why that might be the case? Or maybe you have an argument to say, does it have to be? Tell me. Don't worry, and we will prove. What is your intuition? So we're looking at the optimal value of this deterministic expected value problem, where we threw out all that difficult randomness relative to the optimal value of the full-fledged recourse problem. The question is, if we simplify in this way, do we have reason to think that we actually get a lower bound for the optimal value? Yes or why? Who dares? Your intuition is silent.
You solve a realization of the problem, so as soon as it gets more complicated, the solution can only get worse.
Yeah, so you're looking at a single future, single realization. You know what it is. You can take advantage of that by planning for that particular future. So that will indeed allow you to make better decisions. Better means at lower cost. So that would be one intuitive argument to say, could be that this indeed gives us a lower bound. In fact, we'll talk a bit about it, but the intuition is more likely to be indeed that it gives a lower bound. By the way, I'm introducing notation here. I've been using those acronyms EV for expected value problem, but I will also use it for the corresponding optimal value. Do the same for the two-stage problem, which I denote by TS. Its optimal value is TS. So I can write that EV is at most equal to TS, meaning it gives a lower bound. Yeah, so that's on the notation. Now, let's try and prove this result. And we will be able to do so, but actually, here comes into play the Groningen definition of fixed recourse. We actually use it, as you will see. What I'm saying is that if you do not have that Q is deterministic, the story doesn't apply. provides a lower bound for the optimal value of the recourse problem. And it's convenient to introduce some new notation again. In fact, we'll be using it for quite a bit. It's not very deep. I'm defining a function g of x and omega, which is simply the sum of direct gate cost, or first stage cost if you like, cx, plus the corresponding second stage cost for that particular realization of omega. The value function evaluated in that vector of deviation for that omega in the fixed x. Okay? And moreover, I'm writing x naught to be my primal feasible set defined in terms of non-negativity and equality constraints, ax equal. So nothing new here, just new notation. The reason is that using this notation, I can very concisely write the two problems that we wish to compare. Namely, the two-stage problem and the expected value problem are minimization problems over the same feasible set x naught. That's important to observe. They differ only in the objective. Namely, the recourse problem, the two-stage recourse problem, has as objective the expectation of g. Whereas the expected value function problem, well, expected value problem, has as objective the minimization of the expected value of g. No, that's wrong. G of the expected value. Right? So again, two-stage is minimization of the expectation of g. Expected value is minimization of g of the expected value. All right. What we need to prove is this. Both problems, we assume, are feasible, so they give the corresponding quantity. For the two-stage problem, I denote it by x star. For the expected value problem, I denote it x EV. And our inequality to prove is that indeed g of x EV and mu, which is the optimal value of the EV problem, is a lower bound for the expectation of g in x star. And then taking the expectation with respect to omega. Indeed, the optimal value of the recourse problem. Okay? The question is, how to prove this? Well, it's a difficult question, but we break it in two. Namely, what we're going to prove is that this equality holds for any argument x. Why would we do that? Well, looking at the first assignment, as displayed over here, should we move involves two arguments. It compares some function of x EV and some other function of a different x star. And now I say, well, I'm going to make an intermediate step. I'm going to prove this inequality for an arbitrary x. It always holds. And then I'm done because, well, x EV, by definition, is the optimal solution of that EV problem. And therefore, its objective value is a lower bound for the same function evaluated at x star. Why? Because x star is a feasible solution, but not necessarily optimal. It's for minimizing. All right? And then the remaining step is to say, okay, if I can prove this, then the second inequality follows, and together, of course, they imply what I need to prove. All right? So my question to you is, what can we use to prove this inequality? What do we know about this function g, which tells us that this is actually true?
G is convex, so this one holds by the chance.
Yes. To be a bit more precise, but saying exactly the same thing is this. We do know from our analysis that this function g for any fixed x is a convex function of omega. In fact, our perspective was more of convexity in terms of x, but exactly the same analysis tells us that it also holds for fixed x in terms of omega. So yes, for fixed x, g is a convex function of omega. And now the question is, okay, what do we know about the function evaluated in its expectation versus the expectation of the function given that the function is convex? And then indeed, Jensen is everything that we need. The famous Jensen inequality that you all know by heart, don't you? That is all we need. And indeed, we prove that this inequality holds, and by the argument just above, we find indeed the simple problem that we are solving in the expected value is indeed a lower bound. So we have an upper bound for any feasible solution. Well, since we're solving the expected value problem, we have indeed a candidate feasible solution, namely the solution of the expected value problem. Like any feasible solution, its two-stage recourse objective function value is an upper bound. So, the conclusion of this story is that instead of determining the optimal value of that difficult recourse problem, we can hope to get away with solving the easy problem, taking its solution and plug it in. That's called the expected result of the EV solution. And to do so, we could, for instance, use simulation. It's one function evaluation, so we can afford to spend a little bit of time on it. So then we have an upper bound and a lower bound, and we hope that the difference is small. If so, it tells us the current solution found by that very simple model, the EV problem, is quite a good solution. Since the gap between the lower bound and the upper bound is small, its objective value is almost the same as the optimal objective value. It's feasible, so it's probably a very reasonable solution. Of course, that's what we hope to find. In practice, it's typically not the case. The gap will be large. But at least we've learned something about our problem, namely that for all we know so far, it is actually necessary to solve that recourse problem, that difficult problem. Okay? This kind of approximations of models and corresponding optimal values will be the subject also of tomorrow's lecture, because there's much more to say about it. For instance, on the question, what do we actually mean if we say that the difference is small or large? Is 10 large or small? Million large or small? We need to make more for statement. Yeah, so that will be the subject of tomorrow. We have -1 minute for questions, so I'll see you.